For the reactor to actually fulfill its purpose of creating energy, the fuel that is being used needs to go through a process called nuclear fission. Nuclear fission is the separation of a heavy nucleus spontaneously or from the impact of another particle to produce energy. In our nuclear reactor, neutrons are being fired at heavy uranium-235 atoms to induce fission. Slow-moving neutrons are sent near the U-235 atoms, and some of them begin to capture the neutrons. This puts the atom in a relatively unstable state and raises the probability that the atom will undergo fission. The time when an atom will undergo fission is impossible to tell, but if the neutron being fired is within a certain energy range, it raises the chance of fission occurring. This is dependent on the element being used for fission and the isotope of the element. Once the U-235 has finally undergone fission, it can produce a variety of elements that are usually concentrated around the middle of the periodic table. At the same time, around 2 to 3 neutrons are released from the nucleus. Once the neutrons are released in the reaction, they travel to other U-235 atoms in the reactor, and the process continues, causing a chain reaction. Here is an example of one of the reactions. Although the total energy released varies, the average for U-235 is around 200 mega-electron-volts per atom. This is about 50 times better than fossil fuels, which only release around 4 electron-volts per carbon atom burned.
Why we use uranium-235? Uranium undergoes spontaneous fission at a very slow rate and emits radiation. This means it decays naturally by radiation of alpha particles. It also can undergo induced fission, which means when we shoot a neutron at the uranium, it will cause fission reaction. The more it is enriched, the more of actual U-235 we have, which means we can wait longer to refuel. U-235 is also considered a fissile material. This allows low energy neutrons to cause fission, while U-238 needs a lot more energy to cause a reaction. Also, U-235 is used in thermal reactors because of its ability to undergo fission with low energy neutrons, which is what most reactors that generate electricity are today.
The reactor we will be building is a Generation 3 reactor. Two advantages of using a Generation 3 reactor are a long operational life and more efficient use of fuel. The majority of reactors that are in use today are Generation 2 reactors, though. These Generation 2 reactors currently in use have an operational lifespan of about 40 years. Generation 3 reactors, on the other hand, have a lifespan of about 60 years. For the purposes of our project, the biggest advantage of using a Generation 3 reactor is the greater fuel efficiency they have. Generation 3 reactors use about 17% less uranium per unit of electricity produced. Generation 3 reactors are also acknowledged to be safer than Generation 2 reactors, which is important because of the highly enriched uranium used in this particular reactor.
The most important material needed for the nuclear reactor is the fuel. To maintain the reactor for 20 years without refueling, we base our model off an existing system that can run 20 years without refueling, an aircraft carrier. Using the specifications of an aircraft carrier, we can assume the usage of 150.7 kilograms of highly enriched uranium. The most cost-effective way to procure this much uranium is by buying old nuclear warheads and stripping them of their fissile material. This brings us to about $6 million for expenditures, compared to $63 million to buy it and to enrich it to just 5%. Nuclear reactors usually cost $6 to $8 billion to run, but that counts into the cost of disposing of the nuclear waste. By making the nuclear reactor not require refueling, we can significantly cut the cost of running the power plant down by $48 billion in its entire lifetime.
Safety is a key factor that needs to be considered in the design of any reactor. In this case, this is especially true because the fuel source being used to create a reactor that will run for 20 years without being refueled is 93% enriched uranium-235, which can also be used in weapons applications. For this reason, in addition to the requirements of shielding and controls for core temperature, there is also an additional security measure that is required. Much more extensive background checks would be required, as well as extensive security patrols to guard against any possible terror plots or attempts to steal the enriched uranium.